Hello and welcome to my presentation. I'm Seok-won from Dongguk University, and today I'll be discussing our work on learning representation for multitask learning through self-supervised auxiliary learning. Let's begin with overview. In our work, we propose a new definition of shared encoder's universality in multitask learning and a novel self-supervised auxiliary learning method for improving the universality. Through a series of experiments on various multitask running benchmark datasets, we show that the proposed method improves the performances of the existing multitask running method and easily integrate with them. Additionally, we also demonstrate that the proposed method results in decent quality representation of input data. Multitask running is a machine learning approach where a model is trained to perform multiple related tasks simultaneously. Various methods have been proposed to improve the generalization performance of multitask learning models. However, despite these recent advances, the question of how to improve the universality of the representations generated by the shared encoder has not been explored. To address this gap, we first define the optimal task-specific predictors. Then we define the universality as the inverse of the difference between the loss value of an optimal task-specific predictor and that of arbitrarily task-specific predictor, as shown in these equations. Now, how do we improve universality? Including the universality directly into the running object is computationally infeasible as it requires knowing the optimal task-specific predictors. To overcome this, we use the theorem number 1, which deals with inverse proportionality. This theorem provides an indirect but yet feasible way to improve the universality. Based on the way, we formulate our multitask running problem as follows. First term represents general objective of multitask running, and second term corresponds to auxiliary running part for improving the universality. The optimization step is summarized in algorithm number 1. We performed a series of experiments to demonstrate the utility and efficiency of the proposed method on several multitask running benchmark datasets. Here are the results of our image classification experiments. The gray bar represents the performance of the existing multitask running method, while the colored bar indicate the performance when each method is combined with our approach, or sharpness-aware minimization, or pseudo-task augmentation. As shown in the figure, our method consistently improves performance across our multitask running method. Notably, it achieves the highest performance gains when compared to similar approach, underscoring the effectiveness of our method. These are visualization results of representations generated by the shared encoders with our method. As can be seen, when our method is applied, it can be seen that the classes are more clearly distinguished. In particular, in the case of age classification task, it can be seen that the data are arranged in order of age when our method is applied. These are the results of our scene understanding experiment using NYU V2 dataset. The proposed method showed similar or better performance than common benchmarks in recent multitask running studies such as dynamic weight averaging, uncertainty weighting, and PC graph. Notably, these results were achieved without loss balancing or gradient manipulation methods. Moreover, combining the proposed method with other methods resulted in performance improvements. These results confirm that the proposed method improved performance in the scene understanding task across most cases. Thank you for listening to the presentation. The entire paper is available through the QR code.